This is Teresa Adams, and what we're doing today is finding the domain of a function. I'm going to look at the very basic function, f of x equals x plus 1. This is an equation of a line. What we want to do when we're finding the domain of a function is find the values of x that we can put into our function so that the output will be real numbers. So as I look at the equation of this line, I have a line that looks like this. I'm going to cross at positive 1, and I'm going to have a 1, 1 slope. And as I look at the graph of the function, I realize that no matter what value I put in for x, that every output that I have or every y value that I have will be okay values. They'll all be real values. So for this function, my domain is going to be equal to x such that x is a real number. This is called set builder notation. If you don't like set builder notation, you can write it with interval notation. It runs from negative infinity to infinity. So a real basic function like this, where we don't have to worry about what values of x that will be undefined or won't be a real number, then I can say that it's going to be all real numbers. If my function, say, is f of x is equal to the square root of x, but if I were to graph this function, it would look like something like that. So as we can see from the graph, that I don't get to have any negative x values over here. And in fact, if I were to put a negative x value in here, a negative 1 or a negative 2 or something like that, you'll find that you will have a complex number. And for right now, we want to stay in the real numbers. So we know that the domain of this one is x, such that x is greater than or equal to 0, because you can take the square root of 0. Square root of 0 is right there. And x belongs to the real numbers. Again, this is set builder notation. Or if you'd like to do with interval notation, you have the domain is equal to 0 to infinity, where you do get to include 0, so it's a squared off bracket, all the way up to infinity. This excludes any values that are less than 0. Let's look at a more complex rational function. I have x over x minus 1. Now, if I put in 0, I'm going to be fine. If I put in 2, I'm going to be fine. If I put in negative 2, I'm going to be fine. If I put in 1, however, I'm going to be undefined. So I don't really care what's going on the top. I could put any number I wanted on the top, but what I do want to prevent is I want to prevent the denominator from being 0. So what I want to do is I want to find the restrictions only on the denominator. So I set the denominator x minus 1 not equal to 0, and then I solve for x. So I have x minus 1 can't be 0. Adding 1 to both sides, that means x cannot be 1. This is my restriction. I build my domain from my restrictions. So what I've got is my domain is equal to x such that x cannot equal 1 and x is a real number. So that's the domain for that rational function. Let's look at another function. We have x minus 2 over x squared minus 4x minus 5. Now right now I've got to decide what values in the denominator would make this to be 0, because that's what x cannot be. Those are my restrictions. At this point I can't always clearly see what it is, so I have to factor this. So I know that this factors into x minus 5 multiplied by x minus 1, x plus 1. Now, looking at this, I know that this factor of the denominator cannot be 0, and I know that this factor of the denominator cannot be 0. These will give me my restrictions. X minus 5 cannot be 0, and x plus 1 cannot be 0. So x cannot be 5, and x cannot be negative 1. These are my restrictions. And from my restrictions, I build my domain. My domain is equal to x, such that x is not equal to 5, nor negative 1, but it is a real number. Again, I don't care about what's happening in the numerator, because the numerator, I don't care if it's 0 or not. I only want to make sure that the denominator is equal to 0. What I don't want is the denominator equal to 0. I just have to prevent 0 from being in the denominator.